thank you for coming. This is Monday. You could have stayed home. So let me just briefly introduce myself. We work on basically, I call it processing structure property relationship, digging out the physics from, to help us do better in engineering. So this, I was lucky to early on work on rheology, so that we can understand how we can manipulate structure, and then to learn how ductility occurs. And I was always disappointed that I was not working on elastomers until about 5 years ago. We jumped into this field of fracture mechanics. So this is really new for us, about 5 years old. So we previously have worked out how we should think differently about polymer rheology. And because of our progress on fracture mechanics, I'm writing my second book, which will essentially update, these two books will update many of the books that exist currently. So very quickly, my universe is polymer physics, and there are 3 parts to it. On the rheology side, we ask some basic questions. Then we move on to plastic state. In the solid state, we also have a very essential question to answer. And then finally, today, I'm going to share with you what we've been doing with the last topic I called episode 3 on fracture. In particular, I will talk about elastomeric fracture. But let me first review a few very essential concepts in the next few slides. The last topic was about last item was about chemical bond. So if you look at carbon-carbon bond, depending on the tension in the bond, there are certain lifetimes associated with it. For example, it will take 30,000 years if your tension in the bond is about 1.5 nanometers. So it's still too long for us. Or rather, your wearing problem involves tension that's higher. So it takes seconds or whatnot. In any case, we know what relaxation means, right? We know how we think about relaxation. And we also know how to think about its time dependence. So for example, we can do oscillatory shear, make some measurement, and then do the shift, and then realize, oh, that's how relaxation changes with temperature. So that's something very elementary we know. And I should briefly mention we should believe that this affine deformation in elastomers works very well. So molecular strength follows what you do externally or macroscopically. The bad news for all of us is you can make an estimate and find out the theoretical strength of the elastomer should be much stronger. Okay? Should be about 100 times stronger than what you normally see in your lab. And that's a disappointment. And everyone is currently trying to figure out why this is the case. But that's reality. So the question is why it's so weak, and that's something that we can think about. So today I'm just trying to give you a sense of what I'm trying to do in terms of answering questions about, hey, what's the science behind fracture mechanics, behind fracture? What steps or missteps we have taken that we should recognize? And then what would be good questions we ask in this area? So here's the outline. I will start with a very gentle introduction of what fracture mechanics is. Once you know that, you can probably say, hey, I know more than most people know about the world, because fracture mechanics is something I even shy away 5 years ago. And then I will briefly say a word about the essence of polymer fracture, 2 slides. And interestingly, we have an old way of thinking about it, whereas the newer way is even older. You see this funny thing I want to emphasize. And now I will spend a lot of time reviewing what has been done in the last 70 years. There are 3 topics about rupture, delayed rupture, and fracture. Then I will talk about our approach to it. In particular, our approach discovered that the toughness is largely determined by the strength you have in the system. And moreover, there is a lifetime, there is an internal clock that governs all this process, which has to do with the lifetime of your elastomers through how strong or how long your carbon-carbon bonds can survive under high stretching. And that's a completely new concept, ignored in the past. And then lastly, we'll show that if I have time, in fact, by looking at a variety of experiments, how we can go beyond the previous paradigm. So fracture mechanics, it turns out you worry about it only if there are flaws in your system. So it all started long ago when we worry about your window glasses. We find the window glass is so weak compared to what theoretically is possible. And that bothers all of us, weak by 2 order magnitude. So fortunately, there are people who already start worrying about it. If you dig a hole, a through thickness hole in your material, you find the stress at the 2 corners, the tips can be much higher than the remote load or overall load. So that's a good starting point, except if you look at it, when this hole or this flaw is infinitely sharp, the stress will be infinitely high at the tip, which is annoying. And Griffith, for reasons I need to wake him up from the grave to ask, gee, why that bothers him? It really bothers him. So he decided to work on looking at the effect of having the condition for a flaw that you can pretend by digging a hole, and under what condition this flaw will lead to crack growth. So he worked out an energy argument to indicate that it happens when the so-called energy release rate is higher than surface tension. And there's more work on this side later on, 39, when you consider a very sharp crack, you also find that the stress diverges as 1 over R. So as you approach to the tip, it goes to infinity. And what regulates the strength is the so-called K, which depend on the so-called far field load. So these are all simple mathematical results. What bothers them is the divergence. So Irving comes in and says, oh, no sample can go to infinity when the stress is infinite. Therefore, you must, there must be some way to cut it off. So I will not go into that detail, but except you recognize there are 2 pillars. One is to emphasize the stress can build up through the far field load, K. The other one is the condition for the crack to occur by looking at how the energy can accumulate and be released to pay for the surface tension you create. So in doing that, they have identified the relationship between these 2 quantities and described fracture mechanics either in terms of a critical K or a critical G. I'm going to skip much of what I have to say here because I have very limited time. But basically, when you learn fracture mechanics, there's tons of questions that shows up. I'm not even going to go through everyone, except what I learned, I'm troubled by the fact that there seems to be a confusion about equating cause and effect. They are not equivalent, okay? There are many other questions that I'm listing. The beauty of having a recording is, here is this. So you can show it later if I don't have the time. But in any case, I was very bothered by this. I just showed you the 2 pillars. There is a sense these 2 pillars are equivalent. But from day one, the way I read it, they are not equivalent. They are causally related. The stress is determining everything that's happening. This energy is what is associated with the stress. So let's take the most remarkable case. When you have a sample that you know that there's no flaw in it, it turns out you just need to describe its tensile strength and how much you can stretch. But that's not how we think about rubber for the last 70 years. We thought that rubber is weaker. Remember I said it's weaker by 2 order magnitude. One of the things in our mind is it's weaker because there are flaws. But if there are flaws, then indeed it's not sufficient to just characterize your material in terms of stress, and you have to introduce a length scale, okay? And that's what Griffith did. So the Griffith's discovery of the energy release rate precisely says there is a quantity that controls fracture that involves both the strength and the size of the crack. So 100 years of practice is we suspect there's a flaw. Well, if there's a flaw, why don't I just, and I don't know the size of it, why don't I just do a one that I know the size and learn what the flaw is doing? And then you feed back to the system. The problem I learned again 5 years ago about this fracture mechanics is Griffith was able to tell you, hey, I can tell you what happens when fracture occurs. It occurs when this number reaches some value, which implies that the critical stress is, if this is a constant, then you flip it, it's 1 over square root of A. I call this operational definition. This formula does not give us any sense about the magnitude of GC. You can measure the value of GC, but you don't know what it determined by. So I was very much troubled by this. What determines magnitude, right? That's the key question. So let me briefly review what happens with fracture of polymers. We suspect our dear polymer is flawed. Therefore, as anyone do fracture mechanics, we make a cut and we examine at what stress the crack will propagate. And indeed, you'll find that the stress will propagate if the crack cut is larger. So it says 1 over A square root. So if you make a plot, you find indeed as I use larger crack, the propagation will occur at a lower load. And people were patient enough to use smaller and smaller cut and find eventually it reaches a value when the cut is small enough, your material is as strong as without having any intentional cut. So if you are patient, you will realize following this, that means my equation on the left, I go to the minimum cut size, and on the left it becomes the tensile strength. And if you work out the detail, you will find that this means I can write Kc in a different way. And the textbook, if you analyze this, simple math, you will be able to conclude, oh, the reason there is a minimum cut size is because that minimum cut size matches the flaw size. And turns out that that conclusion is highly problematic. It turns out the meaning of this minimum cut size has a different origin. And I'm trying not to go into any details, but there are later analysis you can analyze. You'll find that the existence of this minimum size is actually related to how sharp that crack is. So if you do that, you find that you can start to answer the question. The Kc in operational way, you don't know its magnitude. But through this analysis, you find this Kc actually is determined by the strength of the material and the sharpness of the crack. I would probably skip most of it. I can find, this is why I said in earlier days, we know this insight much better than Griffith was able to do. So if you have spent enough time to look at this simple solution, you basically imagine I keep loading my sample until my tip reaches the strength. That's when breaking occurs. On the left, you'll find that this will be a relationship between the Kc and the strength of the material. So what we try to achieve, and we did achieve, is in the last few years, we discovered that this Kc and Gc, they are operational definitions. which are useless in terms of teaching me what its magnitude should be, actually have a alternative expression expressed in terms of the material properties, the strength of your rubber, and how sharp the crack naturally evolved to be. So let me just now quickly, with that background, I know it's still rather abstract, but let me try to now jump to the third topic of reviewing the literature. The literature is very rich, 70 years, continuous research for a very long time, since the 50s. What you typically do is you do the tearing experiment. What was found was if you tear faster, you find there's more force arising from the faster tear. So that's one of these lines. And then you find at lower temperature, it's more resistant. Okay? And that's well known for 70 years. What people tend to ignore is a parallel set of the universe where you don't make any intentional cut. You just prepare a nice dark bone or a ring, as we often do. And then, without any cut, you try to stretch until it breaks. So you get tensile strength. And similarly, you find the tensile strength grows with rate and grows as you go to lower temperature. So there's a whole set of data, and I will go to more details later. So people can even make a master curve that I will explain to you. But basically, this plot is plotting the strength as a function of 1 over the rate. So the higher the rate, the higher the strength. And there were some explanations early on about how to understand this, which I will criticize about. So in any case, at the end of the day, there were data that shows this. They even made a 3-dimensional plot showing its temperature dependence and rate dependence. So let me go into a little more detail and first talk about this topic that most fracture mechanic people avoid, which is without a cut. If you don't have a cut, that's not a fracture mechanical setup anymore. Except they blame everything in terms of mechanical response, fracture mechanics, because they visualize flaws in the system. In any case, let me try to tell you what intrigued me, which is known for almost 70 years. If you stretch faster, you find the rupture will occur at a higher strength and higher tensile stress. If you go to lower temperature, you'll find your material is stronger. So these are the two effects that I verbalized there. And there were even some theory trying to explain that, which I will again say I will criticize very soon. So these are the key papers, 58 and 60. So here's the actual data. I was just verbalizing what I told you. So you can imagine a so-called rupture problem. Oops, rupture, right? And it was known since 1960s that if you use a low rate, it will rupture here, higher rate rupture here, even higher rate ruptures there. If you plot these 3 points as function of the rate, you get this line. The higher the rate, the stronger it is. And then the higher the temperature, the stronger it is. So this is the lower temperature. Did I say it wrong? The lower the temperature, the stronger it gets. So this is a lower temperature, this is a higher temperature. Known for nearly 70 years. How to explain it? So I give you 2 literature explanations. First one is due to Beakey and Halpin. He was confused about Beakey, who was a very famous professor at Accra, eventually at Accra, not that time. So he was confused about what creep experiment was teaching him. Basically, he grabbed a piece of sample. He was using constant force, and creep he found, if you had given enough time, it creeped to a point and then rupture occurred. So I replotted his data here. From that, he concluded something that's completely erroneous. And basically he says, oh, I understand what rate effect is. If you use higher rate, then the time you use is so little, the chain has no time to become elongated yet. So let me teach you how this goes, right? So you imagine you do this is essentially I'm doing the microscopic stretching on this side. This is your molecular strand. So I'm just talking about affine deformation. So as I stretch to this point, my molecules get stretched this much. If I use higher rate, he basically says, oh, it takes less time. My chains are not as stretched yet. You need to wait to get stretched. Or so therefore you have to you basically you can essentially avoid being broken because at that time the stretching hasn't occurred yet. Not sufficient stretching hasn't occurred yet. So this is his explanation that the higher rate will be stronger because when you use higher rate, which is red relative to the black, at that point you haven't spent enough time, and therefore chain hasn't stretched. And this goes with the paper, further paper saying that, which is the key mistake, that which we accepted for 70 years, that your rubber is spending most of the time reaching to the critical molecular strand and spend very little time when you reach the critical strand for chain scission to occur. That's the claim. And that claim, of course, completely violates the reality of affine deformation, which is why I reviewed for you what affine deformation is. Your experiment was not a creep experiment. You do a displace experiment. Once you reach that strand, you have that molecular strand already. So let me give you the second explanation. The second explanation was that this problem, seemingly a non-fracture mechanical problem, is a fracture mechanical problem because there's a flaw in there. So they want to explain this rate dependent through a separate experiment where you have a cut, where you learn about a relationship between the energy release rate and the rate of crack propagation. And I will not go much further except to say that this problem is really too difficult because there's no relationship between the crack propagation of a pre-notched sample and the rate you use to stretch an unnotched sample. So, so this is just a good reason hardly any papers study rupture, because we really run into this difficulty. In fact, I probe my colleagues nowadays all the time. I force them to explain rupture. They really give up. I'm not touching rupture. Rupture is difficult to deal with. And in my view, it's clear that it's really difficult to use fracture mechanics to describe rupture. So further, it turns out people collected, I'm re-showing this data, collected lots of this data. They find the strength is changing with rate and at different temperatures, it's getting stronger. And they said, oh, that's in the 50s. WF was just discovered. Let's do a temperature superposition. Let's shift them. And they find if they use WF, you get a curve almost like a master curve. That's published in all the literature. Except if you look a little carefully, if you try to really produce a master curve, you find you need a shift that's different than the WF. Okay, that's the red shift. That give you a much better master curve. And it suggests that temperature dependence is rather different than WF. So I'm just trying to show you that this is the whole literature talking about how we think about rupture in terms of temperature dependence through the WF. The most important experiment, in my opinion, is this delayed rupture experiment. So what the same Smith, what he did was to, and then hardly never repeated. Nobody ever paid attention to this experiment. So that's what he did. And I want to say, to the degree that this book does not even cite this paper. It's pretty remarkable. So let me just try to say what that experiment was, published in 1960. You stretch a rubber to a certain degree, you hold, and wait. Lo and behold, it will break. You stretch it a little more and hold, it takes less time to break. You stretch it the same degree, but at a lower temperature, it takes longer time to break. So he did all set of the state, okay? And he even remarkably anticipated this result after he has done the continuous. So I scratch my head, really try to get into his mind about how he even can anticipate holding a stretched piece of rubber and expect it to break. And the explanation is the same. You stretch. If you do a so-called delay rupture, which usually means you stretch very fast and hold it. Well,
so
yeah.
After you stretch it,
you hold it.
You hold it. There's no further deformation.
Nothing. Yeah. Nothing further going on. This is the most beautiful experiment because there's no ongoing deformation.
I see. And then if you wait enough time.
He waited as long as 7 days. If you don't stretch enough, he was very patient. He's a patient man. So yeah, so it could be second, could be 7 days, depending on how much you stretch and hold, and depending on temperature as well. So the idea I'm putting this into his mouth is if you stretch, the black is the continuous stretching. So until some point it stretch there and break. If you all of a sudden stretch the same level, his idea is the chair hasn't reached the critical strength. So it will take time to elongate. And wait until the elongate. Because most time it was consumed to elongate, to reach the molecular strength, rather than to wait for the bond to break. So my view is exactly the opposite. So that's why he thinks, so look, this is written in the paper. I paraphrase it. Basically it says, the system take most of the time trying to get molecularly stretched than to take time at that stretching to break. And I have evidence to prove exactly the opposite. So this is really beyond one. Sorry. No paper ever repeated this. How to comprehend this? Maybe they didn't figure out this is the reason. So in any case, the same paper speaks about nothing else. Look, last one says the temperature event rupture has no significance. So basically, they are aware chain can break, except they are also insisting that chain breaking is not the dictating process. The system is mostly spending time reaching the stretching, which is a big violation of what a fine deformation is, which actually is quite accurate. I will have experimental proof for you. So in any case, this is the same paper. He did it for different temperatures, so he can claim that there is a temperature dependence of this phenomenon. For example, well, at the lower temperature, it takes longer time because polymer relaxation is longer. So the WF will give you that fit. So he fit them. This is the fit. Okay? And look like, oh, randomly it fits quite well. That's what I mean is the fit, the fit of the red is the red is the WF, and the symbols are the data. Except if you properly shift this data vertically, you find they are systematically deviating. Okay? So let me repeat. So basically, it's the same data. You just need to look at them, and then you realize something is wrong. Now let me talk about the third one. Now it comes to the world of fracture, which usually you mimic that process by doing a tear experiment. The tearing experiment really obscured causality. People thought that how much force is arising is produced by how fast you stretch. Same thing, it turns out the higher the rate you stretch, the faster the resistance. We can talk privately, but this is a big deal that I claim that this experiment was confusing the causality. So I can review for you in the beginning that that's the first paper. Revlin teaches us that we should use a pure shear, except they find that this energy release rate is much higher than surface fracture energy. So these are, I'm just flashing this result again and again, showing you that the so-called energy release rate is higher as you tear faster, and is higher as you go to lower temperature. All this is summarized in terms of this expression, suggesting that there is an additional contribution coming from tearing faster. Because this G is much higher than gamma. So this second term is much larger, which is monotonically changing with the rate, and follows WF. So suggests that this is all viscoelastic and viscous dissipation, in fact. So this is the WF shift here. And there's just tons of work like this. So this is the shift. So they shift it and get this so-called quasi-master curve through WF. So this is, in my opinion, this is where the trouble begins. The G is no longer, the surface tension is much larger. And if you look at it from this energy viewpoint, you have no way other than suggesting that the second term is all dissipating. And that seems to be consistent with the idea that the second term is changing monotonically with the rate of stretching. And therefore, its origin is viscous dissipation. So that's the current paradigm, reviewed and discussed in our textbooks. So you can look at this a little closer, the very same data. You do WF shift, that's how you get. But if you do a little more carefully, as I did, you find the shift is the circles and WF is the blue line. They are not the same. That was just a minor way for me to. Yes, please.
Is this for a filled rubber or unfilled?
Everything I say is gone.
Rubber.
So it's all unfilled at this point. So, in fact, there are theoretical attempts, trying to compute for what this term is by relating this term to the rate of crack propagation. Since you have to think about dissipation, so there you need to convert this velocity into rate. In converting that, you must introduce a length scale. The only length scale they can introduce is an unphysically small length scale. But people are happy you can fit the data. Okay, so they imagine that this crack propagation involves a length scale of 15 nanometers. Okay, so let me summarize now, right? One more time. We blame this the so-called crack speed dependent term in terms of viscous contributions. And as I said, people even computed for how this term depends on the rate by assuming a certain unknown length scale. So that's the paper by someone by the name of North from Caltech. The question really is, what if your physics is such that you cannot write anything in a separable way? You cannot multiply, you cannot add. So in any case, this is my last slide about how they concluded. Same thing, 1 angstrom is involved, and this is all in the framework of calling this energy dissipation. Okay, so that's it. So now comes to what we look at, how we look at it. I have 10 minutes, that's enough, because lots of things are in our publications that I will mention about. So basically, do we have flaws? So we can. This is the same. Okay? So basically, do we have flaws? And how do we know we have flaw or not? So we decided to look at the tip directly and to look at the stress at the tip and to even compare that stress at the tip with the tensile strength. So through that, we can learn about whether flaw is really the problem. Okay, so here is the one that we intentionally make a flaw and stretch it. And so it turns out that you can patiently analyze this movie and find out through birefringence what is the state of stress at the tip. And start to ask the question of why at the higher load, the crack speed is higher. So some of the details is already published in this paper. And basically, one of the beginning effort I had was to clarify the meaning of Revlin Thomas experiment. What they find is they do a pure shear. They find that independent of age, the crack will start to propagate at the same G. Okay, which has the formula has the implication this is all a beautiful energy argument. I had a different insight. I judged that this occurred because when the crack occurs, because the tip hasn't reached the same stress, overcoming the strength of the material. So it turns out we can just repeat this experiment using 3 different heights. We find indeed what you're supposed to see. In other words, if you load your sample with different height to the same overall load, you find the tip is much more intensified when the sample is taller. Okay? Similarly, if you find the crack propagation occurs, you find that's independent of the H you used. And in other words, the higher H, it involves a smaller load. Okay? At the crack propagation, the tip stress condition is the same. So indicating all this is about how the stress is dictating the breakup of the network at the tip, rather than an energy argument. The most remarkable thing out of this was you are able to find that the tip stress grow linearly with this parameter called K that I introduced initially, which basically is the far field load. So this linearity tells us the tip stress just linearly grows with far field load. In fact, you can look at the point where crack propagation occurs and find out that that point, if you regard that as the material property, then you find this linearity actually naturally produce a length scale, which is the material property related to basically how the stress intensifies at the crack tip. So through this exercise, we learned that we previously only know K is determined operational. Now we learned the magnitude comes from the material property. So you have a pair of quantities different than what we knew before. And this is why I said from the beginning that the strength is determining your resistance to crack propagation. So as that's all discussed here, and this is the beautiful result showing you that you can replace this operational definition with the more insightful information about how it depends on the material properties. So in any case, I think there's without question that the problem of fracture is a transition problem. And I'm going to flash very quickly. So when the chain is stretched, you can build force. You can build more force. And if you don't build any force, the bond can survive longer than the known age of the universe. That's textbook. So you build enough force, and this is the density functional calculation showing that lifetime of the bond just crashes down as more tension is built in the bond. So through that insight, I can build a theory about stretching is about the lifetime. Your material lifetime shortens as you stretch more and more. Until that time meets the experimental time you have already spent, boom, break would occur. So through that, I could build a theoretical calculation showing how the rate dependence and temperature dependence takes place. So these are the papers so far, and we're writing more, and these three are unpublished. So if I have a few minutes, I'll just show you this unpublished results. They are none of them has been published. So I will show you that one of the big confusion is about the rate. I will show you evidence against BK and twice. Okay. So one of the confusion in the literature is that they really conflated cause and effect. The Turing experiment was misinforming you about the relationship between G and G is the load, VC is how fast you propagate. And this plot should never have been plotted this way. You should always plot VC versus G. In other words, it's the load that's determining the bond tension, and the bond tension determines the lifetime of the bond, and therefore determine the lifetime of the elastomer. So you can prove that. You can do this by simply load them to different levels. You watch the speed of crack changes with the load. So this actually is a beautiful experiment. We used 4 different rates to stretch this pure shear experiment. And lowest rate versus highest rate. In the region where they reach the same strand, the speed is the same. In other words, the speed of crack is only determined by how much you have stretched. The rate is a variable that just tells you how quickly you get. So details, I guess I get you the sense. Let's talk about the evidence. So this is a movie taken to show the sample being stretched to two very different, with the 2 different rates to the same level. The first one stretched slowly, it broke. The second one, because you haven't spent enough time, so your network hasn't expired yet. Therefore, you can stretch more. And this is the actual result, that we use 4 different rates. If you look at stretching to 1.37 for the 4 rate, they all reach the same level of birefringence, indicating the molecular strand has all been reached instantaneously because it's a fine deformation. And we repeat for the first time the result of Smith and Stedgway about how you stretch the same level at different strands and wait for the delayed rupture, how the temperature dependence occurs, and the dependence is very different than the WL. This is just being submitted paper. So one of the last one is to show once again this beautiful result of what is the essence of the delayed rupture. So on the left, we have a continuous stretching. So let me do it one more time. On the left, we have the continuous stretching. Oops. That's the red. And on the right is the step strand that we did. And then the system just wait until the network expires in the red. Whereas the continuous stretching was so slow, you already eat up all the time. And so by the time you reach the expire, they all expired about 100 seconds. So that actually tells you the structure of my theory. I'm not going into details, but basically you can do this for different rates and find the time scale revealed by step strand waiting versus the time consumed or elapsed during continuous matches. And similarly, the system spent most of time just waiting for the bond to break. There's no change in the molecular strength through birefringence that we can measure. So one of the key conclusions is the separation of time scales. In our theory, it's clear most of the time is consumed by the system waiting for the chain to break, rather than spending the time to reach the molecular strength. So that's one of the key results. I wish I had more time, but I'm running out of time. There were a couple of fascinating transitions, one of which deal with natural rubber. So natural rubber is known for a long, long time. When you change the cut size just by a few percent, it will change the strength of or your resistance to crack propagation in the language of energy release rate by a lot. So this is data. You just, for several different rates that you did this. So this is a pre-cut, and then you basically imagine using a cut size just here or just here. It sharply becomes stronger when it's only a few percent smaller, the cut size. And this can never be, and it's sharp. The sharpness people don't ask the question why it's so sharp. And the whole explanation now find the answer in our theory. The theory has to do with, of course, there is strain-induced crystallization. That takes time. And that process is competing with the lifetime of the network. So depending on whether there is a chance, so the reason you are weak is because the network breaks down before the strain-induced crystallization can take place. And it occurs over a very sharp region, and I plot it here to indicate why it's so sharp, because the two meet in one place only. So with that, I conclude. I think I'm doing okay with time, but this is for the first time I'm reading my conclusions. I think it's very important to realize that this is about what happened. So this is about separating of time scales, and most of the time is spending in waiting for the bond to break. And there is a lot more insight one can have by looking at the English solution. And now we understand not only why G is constant, but we also understand what determines magnitude. So finally, I want to say that the timekeeper in your elastomer is this network lifetime through bond breaking, not polymer relaxation time. So indeed, there were two relaxation times, two time scales, except for 70 years, we've mistaken the time scale to be that of polymer relaxation rather than this lifetime through bond dissociation. In other words, the motion generally is much, much faster. Most of the time is spent on, like Smith did for 7 days, because the tension is not high enough. So he waited for 7 days, boom, break. 7 days. All the molecular motions are irrelevant, as you know it. But yet, they still wait. So that's the conclusion, really.